Have you ever stopped to think about those invisible things all around us, like the buzz of your phone or maybe a distant radio station? What are those things, really? These precise, sort of rhythmic pulses.
They power so much, don't they? Your phone, the radio signals, even the light you're seeing right now.
Exactly. We interact with them constantly, but maybe don't give them a second thought. So welcome, everyone, to the Deep Dive. Today, we're going to try to cut through some of that complexity. We're exploring one of the most fundamental ideas in physics, in engineering, frequency.
Mm-hmm. And it's not just some number on a gadget. It's like the heartbeat of how so many things work.
Right, from tiny particles to huge cosmic waves. We want to go a bit beyond just the basics today. Our mission really is to take frequency and its partners like wavelength and period and make them crystal clear.
We want to break it down, make sure it's really understandable, even if you're maybe just starting to get curious about this stuff.
Yeah, no getting left behind. We're drawing on some really foundational explanations designed precisely for that clarity for everyone. Think of it as building your understanding from the ground up.
Mm-hmm.
Okay, so to really get frequency, we need to start with the absolute basics, right? Vibration.
Definitely. It's the foundation. We've all seen or felt something vibrate. A humming machine, maybe.
Or, yeah, like I said, your phone buzzing in your pocket.
Yeah.
Seems simple, but how do we, describe that motion properly?
Well, think about anything that moves back and forth, repeating itself.
Like a pendulum on a clock.
Perfect example. Or maybe think back to being on a swing as a kid.
Oh, yeah. Okay.
You go forwards, then back, right? Past that middle point and back again. That complete trip, that kind of repetitive back and forth movement around a central point. That's what scientists call reciprocating motion.
Reciprocating motion.
Yeah.
Okay, so it goes away and comes back to where it started.
Exactly. And when something does that consistently, over and over.
We say it's vibrating. Makes sense. It feels like a vibration.
Precisely. And we can start to measure it really simply. Let's say that swing went back and forth 20 times in 1 minute.
Okay, 20 times a minute.
We'd literally just say it vibrated 20 times in 1 minute. That's it. We're counting the cycles.
So just counting how many times it completes that back and forth, that simple act of counting is like the first step towards understanding frequency.
Absolutely. You're recognizing the rhythm, the pattern, and putting a number to it. And what's really amazing when you think about it is how fundamental this vibration thing is. It's not just swings and phones.
Right. You mean like on a bigger scale or smaller?
Both.
Yeah.
You have atoms vibrating, which basically determines what materials are. You have bridges vibrating in the wind, huge structures, even stars, distant stars, they pulsate, they vibrate.
Wow. Okay, so it's everywhere.
It really is. It's how energy moves, how things interact. When we talk about something's resonant frequency, we're tapping into its natural tendency to vibrate.
So understanding this basic vibration helps us figure out how things will behave or even build things.
Exactly. We can predict collapses or design things to withstand vibrations or even use vibrations like in materials that turn a vibration into electricity.
Piezoelectrics, right.
That's the one. So yeah, this simple back and forth is the root of so much complexity, which naturally leads to the question, how do we measure that rhythm more formally?
Perfect segue, because vibration is the what, but we need the how often. And that's frequency.
That's frequency.
So the definition is what? The number of vibrations in a set time.
Precisely. Frequency is the number of times an object vibrates, or you could say completes a cycle, during a specific period of time.
Okay, so back to the swing. 20 cycles in a minute. The frequency is 20 cycles per minute.
You got it. And this applies everywhere. Sound waves, earthquakes, radio signals. If it repeats, it has a frequency. It tells you the rate of that repetition.
Now, in science and especially electricity, there's a specific unit, isn't there? We don't usually say cycles per minute.
Right. We needed a standard. And that standard unit is the hertz. You'll see it written as a capital H, lowercase z hertz.
Hertz. Okay. And that name comes from someone.
It does. It's a tribute to Heinrich Hertz. He was a German physicist, brilliant guy, back in the late 1800s.
What did he do that was so important?
Well, before him, electromagnetic waves like radio waves were mostly just theory. Equations on paper. Hertz was the one who experimentally proved they exist.
Ah, so he actually detected them, measured them.
He did. He showed they were real physical things with properties you could measure. Absolute foundational work for, well, all wireless technology we have today.
Wow. Okay, so every time we see hertz, We're kind of nodding to his discovery.
In a way, yes. It marks a huge leap in understanding.
So let's break down hertz itself. What does, say, 1 hertz mean, like really basically?
1 hertz, or 1 hertz, simply means an object vibrating once in 1 second.
Okay, 1 complete cycle. Back and forth, the whole thing, in just 1 second.
Exactly. 1 full repetition, start to finish and back again, in the time it takes to say 1 Mississippi. It makes it a bit more concrete, doesn't it?
Yeah, it does. Because when we talk about radio waves, the numbers get way bigger than 1. Right?
Oh, absolutely. 1 hertz is a very, very slow vibration in the grand scheme of things, especially for electromagnetic waves.
The ones hertz proved existed.
Those very ones, their frequencies are often, staggeringly high.
Like what kind of numbers are we talking?
Well, it's a massive range. You can have very low frequencies, maybe tens of hertz, used for things like communicating with submarines, because those waves travel well through water.
Okay, tens.
But then you jump way up. FM radio stations, they broadcast around 100 million hertz.
Right, yeah, okay, wow.
Your Wi-Fi router at home, that's probably operating at 2.45 billion hertz.
Billion with a B.
And visible light itself, the light hitting your eye right now, that's vibrating at hundreds of trillions of hertz.
Trillions. It's almost impossible to imagine something happening that fast.
It really is mind-boggling. And to handle these huge numbers, we use standard prefixes, like you hear with computer memory.
Like kilo, mega, giga.
Exactly. So M hertz, MHz, that's megahertz. Mega means million. So 1 million hertz.
Okay, so 100 million hertz for radio is 100 million hertz.
Correct. Then you have gigahertz. Gigahertz, zilligigahertz. Giga is billion.
Like the Wi-Fi. 2.4 billion hertz.
Yeah. And even higher, THz, THz, terahertz. Tera means trillion.
For light, hundreds of trillions of hertz.
Right. These prefixes just make it manageable to talk about a spectrum that covers just an incredible range, from radio waves longer than buildings to gamma rays smaller than atoms.
All described by this one concept. Frequency.
Yeah.
How many cycles per second?
That's the core idea. And this huge range isn't just, an accident. It's why these waves are so different and so useful.
What do you mean? How does the frequency change what the wave is like?
Well, fundamentally, different frequencies behave differently. Lower frequencies, think long radio waves, they tend to travel further, they can bend around obstacles more easily, penetrate things better.
Like the submarine communication example.
Exactly. But as you go higher in frequency, say, up to microwaves or light, the waves become more directional, like a beam. They can carry vastly more information.
Ah, which is why we use them for things like Wi-Fi or satellite TV. More data.
Precisely. And they interact with materials differently, too. Microwaves heat water molecules. Visible light reflects off surfaces, allowing us to see. X-rays pass through soft tissue. It's all down to the frequency.
So the frequency isn't just a number. It dictates the wave's personality, its job.
That's a great way to put it. The frequency is the key design parameter. It tells us how to harness that specific part of the spectrum for a particular job. Understanding that is, well, the bedrock of modern tech.
Okay, that makes sense. So we've got vibration, we've got frequency measured in hertz, and this huge range of frequencies doing different jobs. Let's make it even more concrete. How does this show up in the stuff we use every day?
The radio is a classic example.
Right, you mentioned FM radio frequency. So when I tune my radio, say I dial it to 97.5 millihertz, what's actually happening?
You are physically adjusting a circuit inside your radio. You're telling it to become highly receptive or resonant, only to signals vibrating at exactly 97.5 million times per second.
Ah, so the radio station is broadcasting a wave at that specific frequency.
Precisely. The transmitter sends out that electrical signal, oscillating at 97.5 megahertz. Your radio, when tuned correctly, locks onto that frequency.
It's like they're singing the same note.
Kind of. It's creating a synchronous response. It allows the radio to grab that one signal really efficiently and ignore all the other frequencies floating around from other stations or noise.
So that perfect match lets the music or the voice come through clearly.
That's the magic of tuning. It's all about frequency matching.
And you mentioned FM radio is usually between, what, 87.5 and 108 megahertz?
Yeah. In many places, that's the standard build for FM, which stands for frequency modulation. The information, the music, is encoded by making tiny variations in the frequency itself.
As opposed to AM radio.
Right. AM is amplitude modulation. It uses lower frequencies, usually in the kilohertz range, thousands of hertz, and the information is encoded by varying the strength or amplitude of the wave. That difference in frequency affects how far they travel and sound quality.
Interesting. So the frequency range isn't random, it's chosen for a reason.
Absolutely. Based on reach, how much information you want to send, potential interference, it's all engineered.
Now, in, like, diagrams or technical stuff, frequency has a symbol, right?
Yes, the standard symbol is just a lowercase f. Comes straight from the word frequency.
Easy enough. So if I see F equals 100 hertz.
It just means the frequency is 100 hertz. Simple shorthand.
Okay. Let's talk about the electricity in our walls. This is maybe the most common frequency we encounter.
Definitely one of them. If you look at an appliance plug on maybe the back of your TV, you often see something like 220 V 60 hertz, or maybe 120 V 60 hertz, depending on where you are.
Right. I know the V is for volts. That's like the electrical pressure. But what about the hertz part, the 60 hertz?
That 60 hertz is telling you about the alternating current, or AC, that powers your home.
Alternating, meaning it changes.
Constantly. Unlike DC, direct current, like from a battery which flows one way, AC electricity completely reverses its direction back and forth very rapidly.
How rapidly?
That's what the 60 hertz tells you. It means the current completes 60 full cycles going from positive through zero to negative and back to zero every single second.
60 times every second.
Every single second. It's an incredibly fast oscillation of electrical potential. It's not a steady push. It's this constant, rapid vibration.
Wow. And that's what powers everything. My lights, my computer.
That's exactly what powers them. That continuous rapid change ensures power is delivered efficiently over long distances and allows things like transformers to work easily. Even the slight flicker you might sometimes notice from fluorescent lights is related to that 60 hertz cycle.
That's amazing. So every time I plug something in, there's this invisible dance happening 60 times a second.
It's the silent rhythm underpinning our entire electrical grid.
And it's not always 60 hertz everywhere, is it? I think I've heard of 50 hertz.
You're absolutely right. While North America and some other regions use 60 hertz, much of Europe, Africa, Asia, and other parts of the world use 50 hertz.
Why the difference? Is one better?
Not really better, just different. It mostly comes down to historical choices made way back when the first big electrical grids were being built over a century ago. Different companies, different standards emerged.
And once you build a whole system around one frequency,
it's incredibly difficult and expensive to change. Think of all the power plants, transformers, appliances. So the key thing isn't whether it's 50 or 60, but that it's consistent within a particular grid.
Because everything needs to be synchronized.
Precisely. Generators have to spin at the right speed. Motors and appliances are designed for that specific frequency. If you plug, say, a 60 hertz motor into a 50 hertz supply without a converter, it won't run correctly. It might overheat, be inefficient, or just break.
Ah, okay. So that number, 50 or 60 hertz, is a critical standard for making sure everything works together smoothly.
Absolutely critical. A silent standard enabling our vast power networks.
Okay, so frequency isn't just about electricity and radio waves. You mentioned it applies more broadly.
Oh, yes, absolutely. The concept of cycles per second of vibration is fundamental to understanding other really common things, especially sound and light.
They travel as waves, too, right?
They do. And their frequency is key to their properties.
How does vibration travel, say, for sound? If I clap my hands, how does that sound get to your ears?
Good question. When you clap, your hands disturb the air molecules right next to them, making them vibrate back and forth rapidly.
Okay.
Those vibrating molecules then bump into their neighbors, making them vibrate. And those bump into their neighbors.
Ah, like a chain reaction, a domino effect through the air.
Exactly like that. It's a wave of compression and rarefaction, squashing and stretching of the air molecules that travels outwards from the source. That's the sound wave.
So it needs the air or something else to travel through. It needs a medium.
Precisely. Sound needs a medium, a solid, a liquid, or a gas. The molecules need something to bump into. That's why the classic example is you can't hear sound in the vacuum of space. There's nothing to carry the vibration.
I remember the chair example from the outline, too. If someone shakes your chair, you feel it because the vibration travels through the chair material to you.
Exactly. The vibration is transferred mechanically through the solid structure of the chair. That's a mechanical vibration, just like sound in air. And this is where we see a massive difference between sound and things like light or radio waves.
Okay, what's the difference?
Those electromagnetic waves, radio, light, X-rays, they don't need a medium.
They don't. How do they travel then?
They are kind of self-sufficient. They're made of oscillating electric and magnetic fields that generate each other as they go. They can travel perfectly happily through the total emptiness of space.
Which is why sunlight reaches us from the sun. And we get signals from spacecraft millions of miles away.
Exactly. No medium required. It's a fundamental distinction. Mechanical waves need stuff. Electromagnetic waves don't.
Got it. So back to sound. How does frequency relate to what we actually hear?
For sound, frequency directly corresponds to what we perceive as pitch.
Pitch, like how high or low a note sounds.
Exactly. It's a very direct link. Higher frequency sound waves mean a higher pitch.
Like a whistle or a flute.
Perfect examples. A squeak, a high note on a violin, a small bird's chirp. Those are all high-frequency sounds, lots of vibrations per second.
And lower frequency.
A lower frequency means a lower pitch. Think of a big bass drum, the rumble of thunder, a foghorn, someone speaking with a very deep voice.
Fewer vibrations per second.
Right. So the frequency literally dictates the note you hear. It's the physical basis of music and how we perceive the entire soundscape.
Is there a limit to what frequencies we humans can actually hear?
Yes, there is. Our ears are amazing, but they have a specific range. We call it the audible frequency range.
And what is that range typically?
Generally, it's considered to be from about 20 hertz on the low end.
Okay, 20 cycles per second. That sounds really low.
It is. It's a deep rumble, almost more felt than heard as a distinct note sometimes. And it goes up to about 20,000 hertz or 20 kilohertz on the high end.
20,000 hertz, that must be incredibly high pitched.
Very high. It's like a piercing hiss or whine. And actually, most adults, especially as they get older, can't hear quite that high. Maybe closer to 15 or 16 kilohertz. Kids tend to have better high-frequency hearing.
So our world of sound lives mostly between 20 hertz and 20 kilohertz?
That's the human range, yes. But there's sound outside that range, too.
What's below 20 hertz?
Below 20 hertz is called infrasound. Frequencies too low for us to hear. But they exist. Think of earthquakes, volcanic eruptions, even elephants communicating over long distances use infrasound. We might not hear it, but sometimes you can feel very low frequencies.
Okay. And above 20,000 hertz?
That's ultrasound. Very high frequencies we can't hear. You've probably heard of ultrasonic things.
Yeah, like dog whistles. Or maybe medical scans.
Exactly. Bats use ultrasound for finding their way around and hunting. Dolphins, too. Medical sonograms use ultrasonic waves to create images inside the body safely. It's also used in industry for cleaning tiny parts or testing materials without damaging them.
So lots happening in the sound world we can't even perceive.
A huge amount. And what's fascinating is seeing how this single concept, frequency, applies across all these different types of waves.
You mean like the math is similar whether it's sound or light?
The underlying principles of wave behavior, yes. Cycles per second gives us a common language. Understanding frequency in sound helps us understand frequency in light, and vice versa. It reveals a kind of unity in physics.
So knowing about frequency helps us connect seemingly different things.
Absolutely. It lets engineers take ideas from acoustics and apply them to radio antennas, or use principles from optics to understand seismic waves. It's a truly universal and powerful concept for manipulating energy and information.
Okay, this is making a lot more sense. We've got frequency, the how often, but you said it has dance partners. What else do we need to fully describe a wave?
Two other key concepts that are tightly linked to frequency: wavelength and period.
Wavelength and period. Okay, let's start with wavelength. What does that mean? The length of the wave.
Essentially, yes. Imagine you could freeze a wave in time, like ripples on a pond. Wavelength is the actual physical distance from one point on the wave to the next identical point.
Like from the top of one ripple, the crest, to the top of the very next one.
Exactly. Or from the bottom of one trough to the bottom of the next. It's the spatial length of one complete wave cycle. How much space one full oscillation takes up as it travels.
Okay, the physical distance of one cycle. How does that relate to frequency, the how often?
They have a really important relationship. They are inversely related.
Inversely, meaning if one goes up, the other goes down.
Precisely. Think about it logically. If a wave has a low frequency, it's not completing many cycles each second, then each individual cycle must be quite long or stretched out in space. It has a long wavelength.
Okay, fewer cycles per second means each cycle is longer. Makes sense.
Conversely, if a wave has a very high frequency, lots and lots of cycles packed into each second, then each individual cycle must be shorter, more squished to fit them all in. It has a short wavelength.
High frequency, short wavelength. Low frequency, long wavelength.
You've got it. It's a fundamental trade-off. In fact, there's a simple equation. The speed of the waves equals its frequency multiplied by its wavelength. Speed, frequency, x wavelength.
Oh, okay. So for given speed, like the speed of light, if frequency goes up, wavelength must come down.
Exactly. And this isn't just theory. It has huge practical consequences.
Like what?
Well, remember how low-frequency radio waves travel far and bend around things? That's partly because of their long wavelengths, sometimes meters or even kilometers long. They can diffract around obstacles more easily. But high-frequency waves, like microwaves or visible light, have tiny wavelengths, millimeters down to nanometers. They travel more in straight lines, like beams, and can be blocked easily, but they can carry way more information because more waves pass by each second.
So the physical size, the wavelength, dictates how the wave interacts with the world.
Absolutely. It determines if it goes through things, bounces off, bends around, how much data it can carry. Antenna design, fiber optics, medical imaging, it all hinges on understanding and using the right wavelength, which means choosing the right frequency.
That inverse relationship seems really powerful.
It's one of the cornerstones of wave physics and engineering. The size of an antenna, directly related to the wavelength it needs to catch or send. Why are X-rays good for seeing bones? Their very short wavelength lets them pass through soft stuff but get stopped by denser bone. Why is your phone antenna so small? Because it works with high-frequency, short wavelength signals.
It connects the abstract cycles per second to the physical, how big is the wave?
Exactly. It bridges the time domain frequency and the space domain wavelength.
Okay, frequency is how often, wavelength is how long in space. What's the third partner? Period.
Period. And if wavelength is about space, period is about time.
Okay, time for what?
Period is defined as the time it takes for one single complete cycle of a vibration or wave to happen.
Ah, so not how many cycles in a second, that's frequency, but how many seconds for one cycle.
Exactly. It's the duration of one full repetition.
Can you give an example?
Sure. Think about things that repeat naturally. The Earth spinning on its axis one full rotation takes about 24 hours. So the period of Earth's rotation is 24 hours.
Okay.
Or the 4 seasons, spring, summer, autumn, winter, and back to spring. That cycle takes about 1 year. The period is 1 year.
Or the swing again?
Perfect. The time it takes for that swing to go all the way forward, all the way back, and return exactly to where it started that specific duration is the swing's period.
So in electricity, what's the period there?
For an electrical wave, the period is the time needed for one complete waveform to repeat itself.
Let's use the 60 hertz example again. Frequency is 60 cycles per second. What's the period?
Well, if 60 cycles happen in 1 second, then the time for just one cycle must be 1 divided by 60.
1/60th of a second.
Exactly. The period is 160th of a second, a very, very short amount of time, showing how fast that wave is oscillating.
And the unit for period is just seconds.
Yes, the standard unit for period is seconds. So you see, frequency and period are giving you slightly different perspectives on the same timing. Frequency asks, how many per second? Period asks, how many seconds per one?
They seem like opposites almost.
They are exact mathematical inverses. Period is simply 1 divided by frequency, t equals 1f, and frequency is 1 divided by period, f o 1t. If you know one, you instantly know the other.
So why have both?
Sometimes one is just more convenient or intuitive depending on what you're working on. If you're designing something based on timing a single event like a pulse, the period might be more natural to think about. If you're dealing with radio communication or signal processing, frequency is usually the go-to parameter.
But together, frequency, wavelength, and period give you the whole picture of the wave.
They give you a complete description. How often it repeats frequency, how much space one repetition takes up, wavelength, and how much time one repetition takes, period. They are the fundamental characteristics of any wave or oscillation. Master these, and you've got the toolkit to understand a huge range of phenomena.
Wow. Okay, so we started with just a simple idea like a swing moving back and forth.
Vibration.
Right, vibration. And from there we got to frequency, counting those vibrations, measuring them in hertz.
Understanding that massive range from radio waves up to light.
Then connecting it to everyday things like tuning a radio or the electricity in our homes.
And seeing it applies to sound, too, determining pitch and the limits of our hearing.
And finally, adding in wavelength, the physical size of the wave, and period, the time for one cycle.
Seeing how they all interconnect, frequency, wavelength, period, the complete toolkit.
It feels like we've covered a lot, but hopefully broken it down step by step. You should now have a much clearer picture, feel well-informed about these really core ideas.
You're definitely equipped to see these forces at work around you now.
So here's something to maybe chew on. Now that you understand frequency, wavelength, period a bit better, think about all those invisible waves constantly passing right through you.
Your Wi-Fi signal, phone signals, TV and radio broadcasts, even faint signals from stars.
How does knowing about their cycles per second, their physical length, their duration, how does that change how you think about the seemingly empty space around you.
Does it feel less empty now? What new connections or questions pop into your head when you realize you're swimming in this incredibly complex sea of vibrations?
Something to ponder. We hope this deep dive has illuminated the fascinating world of frequency for you. Thanks for joining us.